Let's check out another example in simple strain. You are watching Mechanics of Deformable Bodies. The problem shows a rigid bar AB, and this is tied on both ends with wires of different materials, different areas, and different lengths. Upon the application of load P, we are to solve for the displacement of point C. We solve this by first creating a free body diagram of the bar. The FBD shows the external load P of 100 kilonewtons and the probable tensile forces of the wires PA and PB. Solve for the forces acting on each wire, so take the moment at point B. Get P sub A times 5.5 meters moment arm from B, and this is equated to the 100 kilonewton force with a distance of 2 meters from point B. Force at point A is then 100 kilonewtons times 1000 conversion factor to newtons times 2 meters. Then divide this by 5.5 meters to get force at A as 36,363.64 newtons. Now that we already figured out the force carried by the aluminum wire, we can either use summation of vertical forces or again another summation of moments to solve for the force at B. In this case, it is safer to use summation of moments at point A. We get force P at B times 5.5 meters as equal to 100 kilonewtons times 3.5 meters. Force P of B is then 100 kilonewtons times 1000 conversion factor multiplied by 3.5 meters all over 5.5, and this gives 63,636.36 newtons. Now compute for the elongation of each wire. Starting with the aluminum wire at point A, where the applied load is 36,363.64 kilonewtons, compute for the elongation by using PL all over AE. That would be 36,363.64 newtons times 2,500 millimeters all over 300 square millimeters times 70 GPa converted to megapascal by multiplying 1000. This is simplified as 4.33 millimeters. Do the same with the steel wire at point B. The wire is pulled by a force magnitude of 63,636.36 newtons. Using the same deformation equation, the elongation at B is 63,636.36 newtons times 4,000 millimeters all over 500 square mm times 200 GPa times 1000 conversion factor. The equation results to 2.55 millimeters. Having the deformations of both wires, we can illustrate them back with bar AB. The exaggerated aluminum wire is 4.33 mm, and the steel is elongated by 2.55 millimeters. Create a triangle from the higher vertex to identify the extent of the displacement of point C. From the illustration, we can visualize the displacement of point C as 2.55 millimeters plus a certain variable y. By the triangle form, we can identify y somewhere at the center, and the other leg is computed as the difference of the two elongations, 4.33 and 2.55, which gives 1.78 mm. By using point B as the vertex for the similar triangles, we can proportion y is to 2 meters as 1.78 is to 5.5 meters. Y is then taken as 1.78 of 2 upon 5.5, giving 0.65 mm. Thus, the displacement of C can be solved as 2.55 plus 0.65 millimeters. That is 3.2 millimeters.